normally use. Let me see. So normally we use something like this. We have efficiency pi d over lambda square. So normally we use this frequency. So this efficiency is this one. So it's 55%. Pi is constant. D is diameter. So this D, this efficiency. Lambda is from the frequency. So this you will get the lambda C over F. Right. So this in linear. So you in dB, you just simply 10 log efficiency pi d over lambda. Don't forget to square. So you will get antenna gain in dB. So this equation will be given. So you don't have to remember. So we didn't use this equation. Okay. In mobile communication, normally you for EIRP, it's always in linear you have PTGT, right? But in satellite, because we need to consider a worst case scenario, we have to consider we have to take into account any losses from amplifier to antenna, because EIRP actually is related to, let me add new. So EIRP actually is from your power amplifier. I would say, sorry. Power amplifier. So we have sometimes we share same antenna with for transmitting, and this for transmitting, and for receiving we have this. So this we use a duplexer. Duplexer is something like a circulator. So the function is to separate between transmitter and receiver. When we use we share a same antenna, or we use one antenna to receive and to transmit. So this when we from the power amplifier, the signal go this way, and then when the signal enter one port of this duplexer, so the signal will come exit at the next port. So this let's say port 1, port 2, and port 3. So from the transmitter, the signal, the wave will enter port 1. So the signal will exit at port 2 and then go to antenna. So we have transmitting. For the receiving signal, so the signal will enter at the port 2 and then will exit at the port 3 and goes to receiver circuit. Okay, so in satellite communication, normally transmitted power from the power amplifier. This PA stands for power amplifier. Normally, the power that given in the specification is saturated power. Saturated power. So this why we call it saturated power. This typical curve for P in over P out. So this refer to power amplifier. P in is input from the power amplifier. P out is output. So there are a linear region, and at the end there is non-linear region. So saturated power actually is on the saturated region. So in satellite communication, we purposely reduce some amount of power so that the operating point of the power amplifier in the linear region. So this the amount of the power reduction, we call it back off loss. So for example, we reduce by 2 dB. So back off loss equal to 2 dB. So this normally in satellite communication, we have a back off loss. So back off loss, I repeat again, is refer to we reduce a certain amount of power from the saturated power so that the power amplifier operate in linear region. So the function is, as you know, that if we operate in the non-linear region, this power amplifier can generate a harmonic signal. Harmonic signal means unwanted signal. So, so it will give you the spectrum at the output of power amplifier become wider because of the generation of there are harmonic signal or unwanted signal generated during amplification. So that's why we need to operate a power amplifier in a linear region. Can you see my mouse cursor? No? Hello?
Yes, Dr. Ken.
Okay. Okay, so so that's related to this power amplifier. We have a back off loss, and then the second possible loss is due to this what we call it a branching loss. So we call it a branching loss. Branching, the word branch, because we branching refer to it's like a what you call it, junction to separate between transmitter and receiver. So this duplexer can contribute a certain amount of loss. We call it branching loss. And then the transmission line that we use normally depend on the if we have high power, then we need to use a waveguide. So waveguide also can contribute a certain amount of loss. So this we call it feeder loss. Okay, so in order to determine EIRP for satellite, so EIRP means we need to consider from this power amplifier until this antenna. And then EIRP normally refer to transmitter side. So we have PT. Then if we have branching loss, so we have L, let's say we equal to LBO. So LBO refer to branching loss. And then we need to minus feeder loss. So this LF feeder loss. Then we have a GT. So in satellite communication, we need, if you are given the branching back off loss, feeder loss, we have another one. What is the another one? Branching loss, LB. So I insert new slide. So we have EIRP equal to PT minus back off loss minus branching loss minus feeder loss plus GT. So that's the three possible losses from power amplifier, which is contribute PT, until we have antenna GT. So this consider your duplexer. So these are possible losses. So depend on the question, can sometime branching and feeder loss they combine together. So it's depend on the question. So if you are given back off loss, branching loss, feeder loss separately, then you have to take into account all the losses. So this EIRP from power amplifier until transmitting antenna gate. So as I said, EIRP refer to transmitter side. So it's not simply EIRP is equal to PT plus GT as you learn in mobile communication, right? So this will be the same in satellite, the same as mobile if all the losses is not given. So we assume that the losses are very small, and then we can neglect. So if you all these losses are given, then you have to take into account. Even though the loss is small, we didn't compare in terms of the answer. So let's say this contribute is there any example? Let me see. I think There is an example, I think it's IRP. So let's say we have this one. Can you refer, slide number 43? Can you see slide number 43? Please respond. Otherwise, I don't know.
Doctor, already.
So let's say we refer to this, we call it parameters for C-band satellite parameter. Receiving also. Because in this slide is, let me see. So in this slide, the transmitter is on the from the satellite. Okay, we have C-band satellite parameter. We have transponder. You can see that the word saturated output power. So it doesn't matter in a station or in satellite. The PT or transmitted power normally you are given in saturated output power. I can give you another. Is there any example for a station or uplink? So this even though there is not stated here, this is supposed to be saturated output power, even for a station, and also from the satellite. You can see there is transponder saturated output power. So I just want to show here from this example. In this slide, there is no branching loss, feeder loss, and back off loss also are there. We have here saturated output power 80 watt. So this actually is downlink power budget is information is come from here. So normally you are given the satellite and earth station parameter. Then this one you need to table up. We call it the limb budget. So limb budget in table form. So this will be provided. This you have to table up the power budget. So from the satellite output power 80 80 watt. So you have to change to convert to dB. So 10 log 80 watt. So you have 19 dB watt. So this back off loss equal to 2 dB. So this is the one that I mentioned just now. We reduce by 2 dB. So this transponder output back off, normally the parameter is given either in table or in sentences. So also this one, not necessarily you are given in table. So sometimes all this information are given in sentences. Okay. So back off loss is 2 dB, and then we have satellite antenna gain on axis 20 dB. So this refer to transmitting antenna gain on the satellite. So the rest is related to other part. So now I just want to show you from power amplifier until we have antenna GT. So we have you are given only one loss, which is back off loss. So in this case, what is EIRP in dB? Please somebody respond. Give otherwise I will call your name. Aiman Fitri. Aiman Fitri. I can't hear you, Aiman Fitri.
Hello?
Yes. Aiman.
Ya, doktor. Tidak.
So what is EIRP for this based on this?
37.
How do you get the answer?
Guna kejap. Guna yang formula ERPPT minus LB. Mana tadi LB? Tu. LB minus
EIRP equal to?
Power transmitted.
I mean, give me the value one by one. Not the final answer.
19 minus
19 minus
2 minus 20.
Why minus 20?
The gain on x-axis.
Why minus?
Oh, what's minus?
Supposed to be plus.
Oh, okay. Plus.
So the minus is if we have loss. So GT is not a loss.
Alright.
So it's the original one is PT plus GT. So if you are given the loss between power amplifier to the antenna, then you have to minus. For PT and GT must be positive. Okay, so that's example how we can determine EIRP from the given parameters. So it depends on which loss are given. Then you have to take into account when you want to determine EIRP. So for other losses, actually it's not related to EIRP, but when you want to determine the receive power, then you need to consider other loss. So the receive power, to determine receive power, you have to this, for example, for downlink. Downlink, at the in the satellite, we have a power amplifier. We have antenna. Then we have receiving antenna again in the earth station. So to determine the receive power, you need to consider all these losses. So all these losses is after the transmitting antenna gain. So it's not related to EIRP. So EIRP normally, as I mentioned just now, is related to back off loss, branching loss, feeder loss, plus GT. So these three possible losses between, after power amplifier until transmitting antenna gain. Okay, so that's EIRP. So related to power amplifier, for your information, in satellite communication, we still use old technology based on non-linear power amplifier. We call it so this normally we use TWTA, traveling wave tube amplifier. So this tube refer to old technology. For example, our old TV use tube technology. That's why you see the old TV set are bulky, because we need to have cathode tube. Okay. So in satellite communication, still we use this type of amplifier because of this amplifier of high gain compared to latest technology, for example, based on solid state amplifier. So solid state amplifier produce a lower gain compared to TWT amplifier. So that's why we say that the characteristic of power amplifier, we have linear region and non-linear region. So that's why we have a back off loss. Back off, we need to reduce some amount of power so that amplifier will operate in the linear region. So that's related to power amplifier. So all these example you can go through. Okay, so so far we talk about EIRP, right? So from power amplifier until we have antenna. So we may in satellite we do have because satellite normally transceiver, we transmit and receive. Sometimes they might share same antenna. We have a transmitter and receiver. So we may use a duplexer to separate between transmitter and receiver circuit. So we have GR is actually a receiving antenna gain. So this LP is a pass loss. So this you use a free space pass loss. So this pass loss normally either you are given the value of pass loss, or you are given the distance. You are given the distance and the frequency, then you need to calculate pass loss for pass loss. So this pass loss contribute the highest loss. For GEO satellite is around 200 dB. So if you get a high receive power or high carrier to noise ratio, you have to check whether you did consider pass loss or not. And then the rest is other losses, for example, atmospheric loss, TA is a losses associated with the transmitting antenna. So this LTA is relate to transmitting antenna. That one is either branching loss, feeder loss. So this the losses associated with transmitting antenna, LTA. For LRA, normally we didn't consider this one because to determine receive power, we stop until at the output of receiving antenna gain. So we didn't consider LRA. LRA is losses associated with receiving antenna. Same thing can be branching loss, LB, can be feeder loss. So, but sorry, this one is not included. So back to this parameter in this slide. So in this slide, this refer to transmitter. We consider transmitter part. You have 80 watt, refer to transmitting output power, saturated output power. You have 2 dB back off loss. Antenna gain on axis mean if we have an antenna from satellite and from the satellite on axis mean if we have the gain from the satellite antenna pointing directly to the receiving antenna gain. So that's referred to, we call it on axis. Transponder bandwidth 36 megahertz. This transponder bandwidth normally give you signal bandwidth. I mean the signal that we send require 36 megahertz. This information needed when we want to determine the noise power. We want to determine the noise power here. But this one depend on the receiver. So this receiver bandwidth. Sorry, we need to consider bandwidth in the receiver, not in the transmitter. So this actually to determine receive power, we didn't consider this bandwidth in transponder or in transmitter. So downlink frequency band, you are given the range, but normally you are given one specific frequency so that you can determine the free space pass loss. For example, here, the free space pass loss at frequency 4 gigahertz. So when you use 32.44 plus 20 log F plus 20 log D, where your frequency 4 gigahertz, and D must be given, then your pass loss will be minus 196.5. So close to 200 dB loss. Okay. So actually, before I go through, based on the given parameter for transponder or satellite, so this refer to transmitter, and receiving C-band earth station refer to your receiver side. So now I want you to tell you that we need to determine the receive power. Okay, so then we want to determine the noise power, so that we can determine what is a carrier to noise ratio. So this the process we call it link budget design. So link budget design, actually you need to put in table. From this table, you can determine what is receive power, and then you can determine noise power. Then you will get the carrier to noise ratio. So in satellite communication, we determine carrier to noise ratio in table form. It's not like in mobile communication. You use equation, right? Based on which model. So you will determine the receive power, and then you minus a noise power, you will get a carrier to noise ratio. But in satellite communication, you need to put in table form. The reason is in satellite communication, because of one part of the either transmitter or the receiver are on the space. Okay, so if we have here, we have a downlink. So remember, we also have uplink. So for uplink, our receiver will be in satellite. for downlink, our transmitter will be on satellite. So if we both uplink and downlink, we involve in satellite, where the satellite in the space is very difficult to adjust the parameter in the satellite. So that's why if we put in table form, it's easy to analyze. So sometimes we need to do recalculation. So it's easy if we put in table form, where in this all the parameter will convert into dB. Then we just add all the parameter. All the negative sign refer to losses. Okay, for example, here we have a back off loss, minus 2 dB. And then we have a free space pass loss, we have minus. And then we have edge of bin loss, minus 3 dB. So edge of bin loss actually refer to, not sure you can see. But the problem is I cannot use my pen. So this refer to your receiving antenna. Receiving antenna is not located in the center of footprint. Let me explain. So if we have a satellite, so we have a coverage area. So we have a footprint. Footprint refer to there is a zone where we have in the center, means if you are let's say your earth station located in the center, that means these two antenna are pointing to each other. So that means there are no loss if your earth station located in the center. So let's say in the next zone, we have minus 1 dB contour. So that means if you are in this zone, your antenna is not really pointing. Your earth station antenna is not really pointing to this satellite antenna. So there is a little bit offset. So this we call it off-axis loss, or in the slide they call it edge of bin loss. Edge beam loss. So this refer to the same thing. Edge beam loss is referred to off-axis loss, meaning your for downlink, your earth station antenna is not located in the center of the footprint. So it's located in, for example, in minus 1 dB, or the next one is minus 2 dB contour. So if you are in this region, the offset become higher. That means your antenna is not really pointing to satellite antenna. So it's depend on the location of a station. So that's refer to age of beam loss. In the sentence, normally you mentioned that your Earth station is located in 3 dB contour. So they mention something like that. So that's refer to age of beam loss of 3 dB. All these losses, when you mention in the sentence, they mention the word loss. For example, back off loss of 2 dB. In the sentence, there is 2 dB is not, there is no negative there. So, but when you put in table, so for any loss, you have to put negative. Right? So in the sentence, they mention the word loss, but the value, the figure, there is no negative, but they must be mentioned the loss. Or sometimes there is no word loss, but we know that that one refer to loss of energy. For example, as I mentioned just now, the sentence say that in the sentence they mentioned that your Earth station is located in 2 dB contour. So that refer to 2 dB contour refer to your satellite, your Earth station location is we have 2 dB loss of axis. So that means 2 dB contour means your Earth station is not located in the center. So your Earth station located in this region where we have off-axis loss or H-beam loss of 2 dB. When you put in the table, you have to put a negative. In this case, -3. So same thing for other losses in the sentence. There are no negative, but in the table you have to put in a negative value. So for any for either downlink or uplink, we start with the transmitting power. So we start with the, let's say we have retro again. So we have uplink, we have downlink. For uplink, we start with the PT in the Earth station. So we have PT. Then until we have GR here. So at the output of the antenna, we will have receive power. So we start with the PT. Maybe in between we have branching loss. Back off loss, sorry. Branching loss, feeder loss, plus GT minus pass loss minus maybe we have atmospheric loss or the other losses plus GR. So this in the equation for for uplink. But as I said, for the satellite, in the satellite, we put in table form. For uplink, we have PT, we have back off loss, feeder loss, branching loss, GT, GR, and we have all other losses. Then at the end, you will determine power. So back to this example. So when you consider all the losses, you can determine what is receive power here. So you can determine what is receive power. So in order to determine receive power, you just simply add together. And 19 minus 2 minus 20 minus 49.7 minus, let's see, okay, 9. So you add together, then you will get your receive power is minus 113.5. Okay, 19 minus 2 plus 20 plus 49.7. So all the plus is referred to PT, GT, GR. The rest must be negative, refer to losses. So your past loss is minus 196.5. So this age of bin loss refer to your earth station is not located in the center of a footprint. And then you have atmospheric loss 0.2 dB. So you have to put negative. And we have other losses 0.5 dB. When you add together, you will get minus 113.5. Receive power must be normally a negative value. So if you get positive, then something wrong. Maybe you didn't include the past loss. So when you didn't include the past loss, you may get receive power positive. Then for so you will get a receive power. Then in order to get a carrier to noise ratio, you have to determine the noise power. So K, Boltzmann constant. So K normally you are given in 1.38 times 10 to the power of minus 23. So you 10 log that one, you will get minus 228.6. So this is a constant. TS depend on your earth station receiving earth station noise temperature. So you can see here receiving system noise temperature TS 45 Kelvin. So 10 log 45, you will get 17.6. So this is how you get TS, is from this information. Receiving system noise temperature TS 45 Kelvin. K is Kelvin, it's not kilo or what. So this 17.6 is 10 log 45. And then BN is you refer to receiving a station about the IF bandwidth for 30 megahertz. So this 10 log 30 megahertz. So this you can see the unit hertz. That means you have to 10 log 30 million, not 30 only. It's different with when you determine the free space path loss. In free space path loss, the frequency in megahertz is different thing. This about the bandwidth. So this how you get 74.8 is actually is 10 log 30 million. 30 times 10 to the power of 6. So you will get 74.8 dB hertz. Then this refer to KTB, refer to 10 log K plus 10 log B plus 10 log KTB. So T. So this 10 log K plus, 10 log K, 10 log TS, 10 log B. So you add together, you will get noise power. So your noise power is minus 136.2. Then your carrier to noise ratio is PR minus N. PR minus N. So you have a PR is minus 113.5. So you will get minus and minus. So noise power must be minus, because you will get a very high negative value for K. So noise power must be always negative, same as your receive power. But noise power normally higher negative value, so that you will get carrier to noise ratio a positive value, because you have a negative. So you have positive, then you have carrier to noise ratio must be positive. If negative, something wrong with the equation or in your calculation. So that's in terms of what is we call it limb budget. So limb budget, actually we want to determine carrier to noise ratio in table form. So we need to table all the parameter, then convert to dB. Then from that we can determine what is receive power, what is noise power. Then you can determine what is carrier to noise ratio. So this actually I skip in terms of this related to limb budget. So this all the parameter. So even though there is a lot of this value, but we only interested to determine carrier to noise ratio. We didn't consider about the thermal noise, carrier to thermal noise ratio, carrier to noise density ratio. So this we didn't consider. So we did consider only this one. So flood density actually is equal to power density in mobile communication. We consider power density, but in link budget we don't have to. There is no parameter for flux density. So we consider free space loss, this TS, noise temperature. Figure of merit for receiving antenna receiving system is G over T. So before I go to G over T, is there any question? Definitely, I'm not comfortable giving a lecture today because of constraint using online class. But I hope if you have any question, then please ask me.
Doctor. Doctor, on slide 43, just now on TS, calculate the system noise temperature. You said that kita ambil system noise temperature daripada receiving C-band punya receiving system noise temperature kat TS yang kat atas tu.
Yes.
Tapi yang kat atas tu dia tulis 45K, yang kat bawah tu dia tulis 58K. So sebenarnya dia 58 ke 45?
58.
Kita kena ambil.
Kat mana? Which one? 58?
Yang kan tadi waktu doktor explain yang TS, calculation TS yang untuk downlink budget tu. Noise temperature doktor kata ambil daripada receiving C-band earth station kan? Dia punya noise temperature.
Yes.
Tapi yang kat C-band tu dia tulis 45K. So sepatutnya dia 58K ke ataupun kita ambil 45K?
48 kat mana you tengok 48?
58. Sebab yang kat bawah
58.
tu kita guna 58. Tapi yang kat atas dia tulis
bawah.
45.
Sekejap. Saya kat mana yang 58 tu?
Yang kat bawah tu, yang second
Bawah.
line from bottom.
Ni,
third line,
74 ni.
sorry. Yang 17.6 dBK tu, TS tu kan doktor kata kita guna 10 log 45 tadi. Tapi bila saya kira 70.6 tu dia guna 10 log 58. Bukan 10 log 45.
Oh ni yang 58 ni. Wait.
Kita ambil 58 ke 45?
Ya. Can you see where is mentioned 58?
Tak ada.
If you 10 log 45, do you get this? Oh, system noise temperature.
Dapat 16.53.
System noise temperature here 58K. So there is, I think this one. Wait. System noise temperature here 58. Receiving. Let me check. Wait. because in the parameter for the earth station, it mentioned about 45. It's not mentioned 58, but when they come with a calculation in the table, it become 58. Let me check with the source, the reference. I mean, so this slide actually you can refer to satellite communication by Pratt. The system noise temperature is 58 Kelvin because the clear air attenuation of 0.2 dB create an antenna noise temperature of 13 Kelvin, which add to the low noise temperature of 45. Okay, supposed to be 45 Kelvin receiving system noise temperature. Never mind. So if let's say you are given the first C-band satellite parameter and receiving C-band station, if you refer to the reference book, he said that 45 Kelvin actually is not the final system noise temperature. It's because of this atmospheric loss, and it will give additional increase the system noise temperature. But it's okay. If you use to determine the receiver noise temperature, if you use a TS equal to 45 Kelvin is acceptable. Okay, normally we just use this value, 45. Okay, either you use 45 is acceptable for this one. 58 actually is the according to the reference book is the correct one. But if you use 45, it's also acceptable. Is it okay?
Okay, thank you, Doctor.
Okay. Okay. So, is there any other question? Okay, in this slide, they mention about G over T. G over T, as I mentioned, is we call it figure of merit to determine the sensitivity or the performance of receiving system. So why because we use a receiving system to in terms of G over T. If we refer to this equation, carrier to noise ratio equation. So as we know that C over N is a ratio of receive power with the noise power. Noise power is KTB or KTSB. So the equation for receive power actually is this. We have PT, GT, GR. We have lambda over 4 pi d. Then we have square. Equal to divide by KTSB. So this this equation actually is blocking somewhere. Supposed to be, it's not. There is must be continuation. It's not showing a full equation for this part. I think this one I convert from Dr. Marwan PDF to PowerPoint. So if we rearrange this one, we have from the one that I wrote just now. We have a PT, GT, we have K and B. And then we have a lambda over 4 pi d square. We have GR over TS. So why we rewrite as this one? Because normally when we refer to downlink, PT and GT refer to the one that on the satellite. So PT and GT is on the satellite. K and B. K is constant. B is depend on the what type of signal that we transmit. So depend on the application. So lambda is depend on the frequency, downlink frequency. D is the distance. So all this one is normally fixed. So the power on the satellite, we fix a certain value. GT depend on the antenna size used in satellite. Frequency also fixed, distance also fixed. So all these parameters are fixed. GR, since GR is a receiving antenna again on the Earth station, so we can, if we want to have a better receive power, we might use a bigger antenna size so that we have a bigger, higher GR. And then TS is depend on the receiver circuit design. So this we as I mentioned, we supposed to study on this one. So based on the one that you have learned in principal communication, normally we consider, for example, this subsection. So normally we determine TS over here. This give you the overall noise temperature is equal to T in. T in is input noise temperature at the output from the antenna. Is consider the noise temperature in the medium, in the air, plus TRF plus T, if you have a band pass filter, divide by GRF plus T mixer, divide by GRF so we have TS. So you have an antenna, then the first part will be amplifier and so on. So we determine the overall TS here. So we have a T in plus TRF plus T band pass filter plus GRF plus TM over GRF multiply with the G band pass filter plus T, what is the next one? Another band pass filter. So the genre is T in plus T1 plus T2 over G1 plus T3 plus G1 G2 plus T4 G1 G2 G3 and so on. So this is something that you have learned in the principal communication. Mine at the end we have Tn refer to G1 G2 multiply with the Gn minus 1. So this how we determine the overall noise temperature depend on number of subsystem. So normally, when we use a high gain, all this part become very low because of the high value of G. Right, so we normally consider until up to 3 subsystem. So the main contribute to noise temperature is the first component. So T1, T2, the number 1, 2, 3 refer to while the first component. So this consider first, second, third, fourth, fifth, and so on. So the first component will contribute the significant overall noise temperature. So that's why the first component normally we use a low noise amplifier. So because of low noise amplifier has a low, this we call it T low noise amplifier, very low. In your principal communication, normally we refer to noise figure. So noise figure for low noise amplifier is very low. So when we have a low noise temperature or noise figure for the first component, the overall noise temperature will be lower. So my point is based on back to this one. TS we can improve or we can lower by choosing the right configuration of our receiver design. So this refer to GR and TS refer to the parameter that we can improve, we can change, whereas the other parameter are fixed. So that's why at the end we say that carrier to noise ratio proportional to ratio of GR over TS, because these two parameter we can change, whereas others are fixed. So that's why we use G over T as a parameter to determine the performance of receiver. Why we call receiver? Because both parameter are related to receiver side. So we have GR, which is receiving antenna gain, and TS is noise temperature in the receiver. So that's why we say that G over T is used to determine the quality of a receiving system. Not necessarily a station, and also for uplink, G over T refer to on the satellite, because the receiver is at the satellite for uplink. So that's why if there is a question that give both a station transmitting a station, transponder, and receiving a station. So they give all the parameter. So you have to know, for example, how to determine G over T for uplink and downlink. I think there is in the slide. Maybe I delete. Or I delete the parameter. This one uplink. a station and downlink a station. Let's say we refer to this one. Let me see. Okay, let's say based on this one, can you determine the uplink G over T uplink and G over T downlink? So if let's say we want to determine G over T for uplink. So for G over T uplink, your receiver, what is your receiver for uplink? Is it on the a station or is it in the satellite? Uh, Anis Suraya. Anis Suraya? Any? So my question is, in order to determine G over T uplink, so our receiver, is it in the satellite or in the earth station? Or I? Are we online or I just talk to alone? Anybody there?
Satellite would be the receiver, Doctor.
Okay, so so what is GR for uplink? So,
31?
where is my 51? 51. How do you get 51?
I said 31.
31. Okay. All right. So yeah, that's correct. For uplink G over T, because it's stated here, antenna gain on axis for in bracket transmit and receive. That means on the satellite. So we have GR and we have a downlink GT. So GR and GT are the same, 31 dB. So for uplink G over T, that's yes, correct. 31 minus what is TS for uplink? Anyone? So I don't have to call the name. 31 minus what is uplink TS?
26.99.
How do you get 26.99?
10 log 500 Kelvin.
Yes, that's correct. 31 minus 10 log 500. So that's your uplink G over T. How about downlink G over T? So for downlink G over T, you have to refer to downlink a station, GR. Here, because you are given efficiency, you have to calculate. I think you need. I mean, it should be given the diameter, the frequency are given. Diameter. What else? Yeah, that's efficiency, frequency. Then from that you can determine GTR for downlink. So in this from this slide, you need to determine. You need to calculate. The one that you mentioned. I mean, GR is equal to 10 log efficiency pi d over lambda square. So efficiency, so 10 log 0.65 pi d should be given. What is the diameter? And divide by lambda is from given frequency, you can determine lambda is C over F. 3 times 10 to the power of 8 divided by 11.45 times 10 to the power of 9. So that's give you lambda. Then you square. Then you log, then multiply by 10, you will get GR in dB. And then you have to minus GR minus 10 log TS. TS is noise temperature here given 33. Okay, so this value GR in dB minus 10 log 33. So you will get downlink G over T. So in satellite, we have different, what you call it, CNR for uplink and downlink. Because of we have a different frequency. So in this case, we have a downlink frequency 11.45 gigahertz. So uplink frequency is 14.15. 14.15, 11.45 for downlink. So you can see that we have a different the different frequency. Then it will give you different pass loss. So that's the what I call it, the main difference between uplink and downlink CNR. Besides, we may have a different gain for earth station antenna. For example, here you get if you refer to an antenna diameter here, D is 5 meter. But for downlink a station, I don't know, is it the same diameter? Maybe the same. If even we use a same diameter, but you can see that aperture efficiency for uplink a station 68, for downlink 65. So even we use same diameter, due to different efficiency and different we call it different frequency, which is a different lambda. So it will give a different gain, right? For a station antenna, for a station uplink antenna and downlink antenna. So that's contribute different CNR for uplink and downlink. Compared to cellular system in mobile communication, we didn't, we normally determine only downlink CNR, right? From our base station to handphone. So we normally determine CNR for downlink. If we determine the CNR for uplink for mobile communication, is almost the same thing, because it's referred to the, in terms of frequency, it can be the same. If we use the same frequency, maybe we use a different time slot, different code, right? So it gives almost the same CNR for uplink and downlink for mobile communication or cellular telephone. But for satellite, we have different uplink and downlink CNR due to different frequency, different, maybe different gain of the station. So that's the difference between satellite communication and cellular. So back to this, in terms of frequency, I think I did ask during a face-to-face class, why uplink frequency always, the first question, why different frequency should be used for uplink and downlink? Why we need to use a different frequency for uplink and downlink? Farah?
Power, doctor.
Sorry, power?
Back to the power.
Power. Apa maksud dia power tu? Any explanation?
I'm not sure, but as I remember, you said that because the ground station we can use higher power, so we can utilize higher frequency. What?
Okay,
That's what I remember. Not sure about that.
So the first question, why we use different frequency? Because we want to avoid interference. And then my second question, why uplink frequency always higher than the downlink frequency? Because of when we use high frequency, the pulse loss will be high, right? When we use high frequency, pulse loss will be high. So for uplink, even why we use a high frequency for uplink? So if we compare with downlink, that means uplink pulse loss will be higher than downlink pulse loss, right? because of higher frequency for uplink and lower frequency for downlink. So, but the higher pass loss for uplink, we can compensate by using high gain and high power on the transmitting station. Because for uplink, high power transmitting power and transmitting antenna gain, we didn't have a constraint because of the transmitter station located on the earth. Compared to downlink, where our transmitter on the satellite. So we have constraint in terms of antenna size. Back to the introduction in our lecture today. If we use, if we want to have a high gain, we need to bring or to, we have to use bigger antenna on the satellite. So if we use bigger antenna on the satellite, it will put more weight on satellite. Consequently, we increase the cost for the satellite. So that means we have constraint on the satellite to give what call it to have a better or higher gain and in terms of high transmitting power. So that one is a constraint due to PT and GT on the satellite. So that's why we need to use lower frequency for the downlink. So you might ask, we can increase GR here, right? But depend on the signal. If we use, if the signal that receive at the receiving antenna gain, the signal is lower than the sensitivity. So it doesn't matter how high gain that you use for the receiving station. Is useless because the receiving antenna gain will increase the receive signal and also the noise signal, right? So that's why GT play an important role to make sure that our receive signal that being received at the receiver should be above sensitivity or above threshold. So I hope you understand my explanation. So back to in the simple word, why we use a high frequency for uplink, because we didn't constrain to have better, higher PT and higher GT on the receiving, on the transmitting station. Whereas for downlink, we have a limitation to have a high GT and high PT, so that we use lower frequency that contribute lower pass loss compared to uplink pass loss. So I think I did cover for uplink and downlink link budget. And so I report again on the limb budget. So you need to table up all the parameters, something like this. Sorry. Yeah, something like this in order to determine the receive power, noise power, then you will get the carrier to noise ratio. So it doesn't matter for uplink and downlink. So for uplink, that means for PT, you take from transmitting a station. So you start from transmitting a station until receiving antenna gain on the satellite. So the different in terms of pass loss. So you need to use uplink frequency, and then depend on the given parameter. So there is a question where you are given carrier to noise ratio. So if you are given carrier to noise ratio, sometimes we take this example. Sometimes for downlink, you are not given the transmitted power for this transponder. So you are not given this what call it, the transmitted power. Let's say in this example, let's say we let me add one blank slide. So let's say PT of a transponder is not given. You are given downlink CNR, they say is 20 dB. So when you ask the question asks you to design limb budget, downlink limb budget. So you still start with the PT. So once because our PT is not given, so you just put PT. And then what else? Back off loss, and let's say, yeah, back off loss. LBO -2. The rest you just follow. Let's say GT. GT 20 dB, that is plus. So at the end, you will get your receive power is equal to PT minus something. So can you? So you ignore now you become 19 dB. What is you put just PT because we don't know. So, hey. So this is PT. So in here, PT is equal to minus minus 2 plus 20 plus 49.7 minus 196.5 minus 3 minus 0.2 minus 0.5. Or this one, you have to minus 113.5 plus 19. Well, what is the value? 113.5 plus 19. 113.5 plus 19. Minus 113.5 plus 19 minus 94.5. So you will get on the receive power column is PT minus 94.5. So your noise power still the same. So we assume noise power still the same, which is 136.2. 136.2. So CNR is equal to PR is PT minus 94.5 minus noise power, which is 136.2 minus 136.2 is equal to given here 20. So you can determine what is PT. Okay, PT is equal to 20 minus 136.2 plus 94.5. You will get PT because you are given CNR. So from that, you can determine what is a receive power. So from PT that you obtain from here, you substitute in this one. Then you will get PR. So that's another type of question. So in this example, I repeat again, you are given CNR for downlink, even for uplink. So you may not given, you need to determine PT, for example. Right? So that's another type of question. So we use this formula to determine overall CNR. So we have, so far we consider CNR uplink, CNR downlink. So this one, if we have more than 2 station, but normally we consider only 2 station. So we use this formula. So this formula actually is in linear. So this formula is come from here. 1 over CNR overall is equal to 1 over CNR uplink plus 1 over CNR downlink. Okay. So if you want to, then from here, you will get here. So this you go up here. And then, I mean, this one, you go to this side. And then this one, you move this side, so become 1 over all this thing. So, but these two value are linear. The calculation are linear. So that means you have to convert. So let's say you know you are given uplink and downlink CNR. You want to know the overall CNR. So you have to convert uplink and downlink CNR in linear. I think there is an example here. So in this example, both uplink and downlink CNR 20 dB. So you need to determine the overall CNR. So either you use this formula or you can use this formula. So the point is you need to convert 20 dB to linear. So this in linear actually is 1 over 100. 1 over 100, you will get 0.01. CNR overall is 1 over uplink. So you convert to linear. So, and same thing for downlink, right? So 20 dB you convert to linear is 10 to the power of 2 or 20 divided by 10. So 1 over 100. That's why you will get 0.01. So same thing here. So this you change in dB to linear. So 1 over 0.01. So this the bottom one 0.01 plus 0.01. So 1 over 0.02. You will get in linear. So first you will get in linear 50 dB. Then you 10 log 50. Then you get overall CNR in dB. Get 10 log 50, you will get 17 dB. Right? So that's
Doktor,
yeah, sorry.
jawapan tak kisah in linear ataupun in dB
If let's say didn't stated, then you can give in linear or dB. Normally CNR should be in dB.
Doktor, saya ada satu lagi soalan yang berkenaan soalan tadi yang doktor bagi, yang dia kata assume yang PT transponder not given tu. Okay, macam mana kita nak tahu based on, based on doktor nak cari value of CNR, nak cari value of PT menggunakan formula CNR, kan doktor tolak, kalau kat sini kan dia given, kita tahu yang negatif 113.5 tolak tambah dengan 19 dB dapat negatif 94.5 tu. Tapi if it's not given, macam mana kita nak tolak? Maksudnya macam mana nak pakai formula CNR tu yang PT tolak value 94 tu? Itu soalan saya.
So back to refer to the question. So that means you are given CNR, right? Downlink CNR.
Yes.
And then PT is not given. So let's say in here, transponder saturated power is not given. You don't know this value. But you are given downlink CNR equal to 20 dB. Okay?
Okay, doktor.
Then when you table up your downlink power budget, for this parameter, you still you have to put PT, but the value you are not given, then you just put PT. You put PT here.
Okay, faham.
So the rest are the same. So that mean how to get the PR is